So today I have one main goal, is to, let me see, actually, slideshow, is to kind of talk about how to integrate GeoGebra into geometry curriculum. Just a little bit about myself. My first experience with GeoGebra was in 2010. I taught in Broward County, actually, and they had someone come in and kind of teach us about GeoGebra. And we were having laptop cards at that point. So we really didn't get it to do it very often, but it kind of sparked it in my mind. And then I got my master's of science in teaching at FAU. And that's where I really studied GeoGebra in depth. I basically, when I describe this to my students, that I tell them that I got my master's in GeoGebra, because between classes with Kasha, Dr. Voss, and Dr. Yu, we did so much GeoGebra. And I really saw how you can integrate, technology into the classroom, but you can make it in a way that's useful. It's not just a graphing calculator or, going online and Googling something. It's actually integrating technology. And I love GeoGebra so much. I have two small children, and most people say that, their ideal kind of trip would be to go lay by a pool or something like that. My ideal trip would be to have like 5 or 6 hours to myself to just explore GeoGebra, because I could just go down a rabbit hole of looking for so much stuff and creating. So maybe one day I'll have that opportunity to be able to spend a lot of time searching on GeoGebra. But in the meantime, I'm going to show you what I've done so far in the time that I have had. Lastly, I teach geometry, algebra 2, and pre-calculus at a high school called A.D. Henderson FAU University High School. So let's get on with it. There. Okay. So my first example has to do with coordinate geometry. Things about proving lines parallel and perpendicular, showing the graph between what does opposite reciprocal mean and what does it mean visually, like the right angle. You can use it as a discovery tool to prove triangle congruence, properties of quadrilaterals, and angles formed by parallel lines cut by transversal. Because if you have parallel lines and you have consecutive interior angles, that you can help to prove all different properties of parallelograms. And in my eyes, a big part of geometry is proofs. What it does is it translates the abstractness of proofs, like the two columnists, into clickable moments. So when they write that reason that, opposite sides are parallel, they're writing on the reasons column, they can remember in GeoGebra, oh, they found the parallel lines. They calculated slope, either using a tool in GeoGebra or actually calculating the slope. Before doing these with your students, I highly recommend making them have an account. I've done it both ways. And what happens if they don't have an account, if the kids log out or exit out, it doesn't save their work and they have to log in again. So you'll get like Maria 1, Maria 2, Maria 3, and then it'll just kind of, each Maria account will have different activities completed. But if they have their name, they can come and go and complete it as they want. So this first link here is to coordinate geometry. And as you can see, I am a thief on GeoGebra. I do take lots of other people's activities, and Tim has amazing ones. So this one is definitely with a highlight to Tim. And I've broken it down into 4 different exercises. So I'm just going to kind of click on that link here and bring you to what it kind of looks like overview. And again, this is my point in doing is just like, I find GeoGebra overwhelming sometimes because there's so much to do and you don't know where to start. But I found that I just kind of pick something, personalize a little bit, and throw it in the classroom. And then from there, you can look at what you want to do differently or what you would add or add your own stuff. So I've broken into 4 different exercises. The first exercise just talks about opposite sides parallel and proving it. And you can see that here's the construction. They can play around with it to show physically, like let's make an opposite side, make a point, make a line, use a segment tool. And then here they are instructed to make a 2-column proof underneath of it, right? Or not a 2-column proof, I'm sorry, just a proof. And this is very loose proof. In when I did in my class, I did sort of as an exploration. So they have the option of writing, as you've learned earlier in these little note boxes here, or as my students love to do, is do it on their paper, then take a picture with their iPad, and you can upload a picture directly in image. The second exercise is very similar, except they've given you the diagonal and they tell you the diagonals bisect each other. And you're going to show it's a parallelogram. Okay. And again, you're going to do a very loose proof afterwards. And I say loose because I'm going to show you my students' work afterwards. The third one builds on it and it says, okay, now you need to plot all 4 points. And no coordinate can be displayed more than once. So basically it can't be vertical and horizontal lines. It needs to be very like slanted. And again, you do a little proof. And again, these boxes here are great because the kids can either, if they have an Apple Pen, my kids use iPads, they can write directly in the box or they can write on paper and upload, like I said. And this one has 2 different ways to prove it, okay? And the last exercise you have here is you're taking the same, but now you're doing a rectangle. Now you're proving a rectangle. And again, no coordinates can be displayed more than once. So what does this look like when a student does it? So from the teacher's end, right? So student work exercise 1. This is the one where they're showing that it's a parallelogram. And this person, these 2 people, I'm sorry, 2 students chose to do the opposite sides are parallel and they show the slope. And a lot of them don't show the work for slope because you can just count on the graph. Or they show that you have the same pair of lines that are congruent. So that's one thing. Again, my goal is for them to visualize when I do my proofs, why are these reasons I'm putting in my proof, why are they the way they are? So if they're, doing the EOC and they have some options, they're going to pick the ones they remember doing in GeoGebra. Another for exercise 2. So I've highlighted this box here in red because that's wrong. And this is a moment where I would, and when I did do this, I went to that person, I went to the table, we were working outside at like little picnic tables. And I was like, ask them like, what went wrong here, right? And I won't expect you all to know because you saw the activity of maybe 20 seconds. But what happened is they gave the diagonal this one, but the person used the diagonal as a side of the parallelogram. So they incorrectly use it. The student on the bottom shows you correctly how to use the diagonal as a parallelogram, and then has used a slope tool. So you can see here, I can annotate the screen, draw. There's a slope tool, and they, I don't know if you can see, use this correctly to use a slope tool. So that's a tool you can embed. And the great thing about GeoGebra is you can create your own tools that will add to the toolbar. And you'll see that later on in the presentation. I've done that with triangles. Okay. So let's see, the next slide would be this one, which is exercise 3. And again, these are not much proofs, right? This is not 2 column proof. It's not even a paragraph proof. I'm not claiming they're proving anything, but it is their basis for a proof. I'm going to clear these drawings here. It's a basis for a proof, right? That is a huge part of the curriculum. All right, now I'm just drawing all over everything. Right, so it reinforces the reason for a formal 2 column proof. And then exercise 4, this is where I would choose, and I did, I paused the activity because this is the one where they make a rectangle with different coordinates. And about 50% of students were not doing this correctly. They were doing it so the rectangle was, horizontal or vertical aligned. So everything, the slopes would be 1 and 0, which was not a part of the curriculum. What was going on here is I wanted them to do it at an angle so they could calculate slopes and show opposite reciprocal. So this is a cool feature, is the pause feature. You can pause everyone and address everyone as a group. Okay, so that's the 4th exercise. Now, again, I showed this example and I said I want it to be for people who are just new to using GeoGebra in the classroom, but I wanted to give an example and tell you why I chose these specific, because I use it in all of geometry. Transformations is huge, use it in that. Definitely in circles when you do that. I might use it in algebra too, I use it in pre-calc. But why I chose these examples, because as you can see, I highlighted, this is the percentage of the test that each different standard is made of. And you can see 46% of the standards came from coordinate geometry. All of these come from coordinate geometry. So for example, oops, these are some specific standards I highlighted here. Let me see if I can find, I circled some of my own that I thought was very interesting. So just the idea of, let's see, proof theorems about parallel and parallelograms, right? Or another one that I highlighted here was the use of a geometry software, which I know on the EOC is different from GeoGebra, but at least it kind of clues them into it, right? What is a compass, not hand on paper? What does it look like on a program? So these are all the standards from that previous slide that make up 46% of the test. Now, I do know they are doing away with the geometry EOC, I believe. They're going to do something different next year, but I'm sure that these ideas will still be very important geometry because they're ideas that carry over into later parts of mathematics. So they shouldn't be gotten rid of. So I gave you an example, right? The one with coordinate geometry. Told you why I'm showing you specific ones. It's such a big part of the geometry curriculum, specifically the EOC. And it allows students to use sort of hands-on calculations, use these clickable moments to carry over to proofs, which again are a huge part of all levels of mathematics. So let me clear the screen because those little blue bubbles are really annoying, and show you my second and final example. So this one is actually a book. Let me just get my paper up here. I made some notes for myself I wanted to talk about. And this book is talking all about triangles and the different centers of triangles. When you tell students that a triangle has more than one center, it sort of blows their mind that any shape could have more than one center. And to be perfectly honest, this topic is tedious. Circumcenter, incenter, orthocenter, centroid, they sound very similar, and it's really easy to get them confused. And as you saw in the previous slides, it is a big portion of the geometry curriculum. And this actually particular book I actually made in parts of it in graduate school. So part of in my MSc program, part of this I've been working on for a while. So it was really cool to actually use it with my students in the classroom. And it's just another way to let them explore, come up with the theorems themselves, right? This whole exploration idea, and maybe in the end, be able to remember it or derive reasons when they're faced with a test, right? So this is what the book looks like. Let's go to it actually. I think that, yes, you can see this. If I do this, maybe it's bigger. I think so. Yes, okay. So table of contents. And I know that in Ed's presentation and probably other people, they talk about books. So this is a book that I did not include notes the way he did, because when I made this, I didn't know about that. I just uploaded a PDF of the notes I use to teach. But there's contents. The contents are first perpendicular bisector theorem, which is really cool because it forces them to realize that any point on a perpendicular bisector is going to be equidistant from both ends of a segment, no matter where you go. And after the book, I'll show you different student works and what I ran into problems, what I was looking for. So if you use this in your classroom, you could be on the lookout. So again, just a lot of what do you notice, right? I love the problems of what do you notice, what do you wonder? I learned a lot from illustrative mathematics. So, and then you take what you notice and you put it into a 2-column proof. And in this one, we actually did the 2-column proof together as a class, and I'll show you that. So this is the first part. Once we get past the perpendicular bisector, we can talk about the circumcenter. Again, these are all made by Tim, amazing applets. I don't know what I would do without them, but it builds it for you, right? And the cool thing I love about this is it's hard to remember that the circumcenter is equidistant from the vertices, but it shows you in terms of that circumscribed circle. And it asks students later on, you'll see, with the purple circle, what's special about the purple circle? And you'll see that people make the leap, and this is, I'll show you, that the radius of the circle is the same at all the vertices. And that's another way for them to remember it, to know why it is the way it is, right? Not just, oh, it's equidistant. And again, there's just lots of questions here. Now, one thing that is really faulty about this page that I would change, I learned this last year's GeoGebra conference, is that for every picture you have there, you should only have like 2 questions beneath it. So students will have to scroll up and down from the picture to their question. So this is too many questions. I would definitely change that in the future. And then the third page of the book is the in center. And again, it's step by steps. You drop the perpendicular. What do you notice? Experiment. You can always jab the vertices. So, if something works for one triangle, you have to wonder, does it work for all triangles? How about acute triangles? How about obtuse triangles? How about right triangles, right? Because we all know that these triangle centers have different properties based upon what type of triangle is. Are they outside? Are they inside? Are they on? This one has, again, limited tools. So you can use the circle tool, or you can do distance or length. You want to say, oh, let's see, what's the length of these, right? Are they going to be the same no matter what? And they can hypothesize. And it's not a proof, but it's pretty good knowledge, right? And let's see, the ortho center. Sorry, there's just a few more pages in this book. I thought it'd be interesting to kind of go through what actually is in here. Talks about one that, I don't know, this is not my favorite. I do have a favorite, is a centroid, I'm not gonna lie. It's almost best for last. Talking about the centroid, how it's created, where it lies based upon the type of triangle. Not too many questions here. And then the centroid. So this one illustrates the creation of the centroid, and it illustrates, as you see, the 2-to-1 rule or the 2/3 rule. You can see that when you create it, you get one segment and then the other 2 parts, and they're all congruent. And this is a huge one on the EOC. They use coordinate geometry to find the coordinate pair of the centroid, given the vertices of a triangle and things like that. And I'll show the student work for how they work through that. And it goes through the ratios, right? What do you notice about your results? What do you notice? What do you wonder? And then can you summarize it, right? Okay. The last one is Euler line theorem. And this is, I think, maybe not in the curriculum, but I really like this because I'm biased. I did make this. But basically you have a triangle, right? You can click that HG and O are there. And there's, in the background of this one, there's tools for making the circumcenter, orthocenter, and in-center. And you can draw the Euler line. And the question is if you don't draw it, what do you notice about these points, right? And then it asks you, and the second question, to add it, the line, and say, does it hold? Are they all in the same line? So that's the top 2 questions. The second questions, and I couldn't get these to uncheck. I feel lame that I couldn't do that. Talks about, can you measure the distance? So again, you have that distance tool. You can go to HG, find the distance, and then you can do the distance for GO. And this is property of one of the many properties of the Euler line. And they're going to find the ratio of HG to DO and say, no matter where the vertices are, does it hold? Is it always that 2-to-1 ratio, right? And then lastly, it talks about the Euler line and where it actually does exist and where it doesn't exist. So it asks them, okay, make it there, draw the points, draw the line, play around, right? And in hindsight, I probably would have added angle measures here so you could see what kind of triangle the Euler line does not exist for. And if I can make it close enough, again, I wish I had the angle measures. You can show that about at an equilateral triangle, it doesn't work, right? Oh, wrong. Oh, sorry, my bad. So that's the last one, okay? And then I linked the notes, but in hindsight, after Ed's talk, I definitely will start doing notes the way he did, which is excellent. So cool that the kids can just write in there on their own, download them. So let's talk about the student work. What would that look like that correspond to this? Let's see. Okay, perpendicular bisector. So here I put the first one in red, as you can see. Where's that little like tool where you can make a little wand? I don't know. It's on my iPad, but it's okay. Oh, I didn't mean to do that. There. Oh, no, I gotta go back. Sorry. I use a dinosaur and I usually use PowerPoint. This is the first time using GeoGebra. Google Slides. So I apologize for my not good working of Google Slides. I just feel really at home with PowerPoint, but I knew that I needed to do this for, where is slideshow? Oh no. Oh, there it is. Okay. There, okay. So I highlighted this left one in red because this person did not get the point. They said that it holds true for every point on the perpendicular bisector, but doesn't hold true regardless of where point C lies. So in this one, I think that they didn't get the message that C was always on the perpendicular bisector, right? So if you see student 3 though says, yes, no matter what point C is, as long as it's on the line, then AC and BC remain equal. And this is the proof we did as a class. So we built this together. So every student, this is a very in-depth one. Eventually they were assessed on this sort of proof, sort of like a fill in the blank, drop down box sort of thing as the EOC is. But this is the end work of what I would like for them to have. So that's for a perpendicular bisector. Let's see. The next one is circumcenter. And you can see what I did here was I did a flow of this first person student 20 is kind of like a very loose definition. Yeah, the purple circle always intersects the vertices. That's what I noticed. And that's okay. It's a level 1 definition, right? Then you go up a little bit and you said, oh, the purple circle shows that the circumcenter is in the center of it, right? And it goes to the vertices. So we're a little more defined here. If it goes to the vertices and it goes to the center, we're creating the idea of a radius. And that's what student 26 does. They say, oh, it shows a radius, right? Student 2 sums it up and says, guess what? It's a circle. The circumcenter is at the center. The radius is shown. And what it does is it proves the vertices are equidistant. So I thought that was beautiful. If I could show this, I show this to my students, I'll anonymize the names and I will go through the different responses of how people came up with the actual most concise answer. So I thought that was pretty cool. And there's a little image of that purple circle in case you forgot what that looks like, which you probably did. Okay. The next one is centroid, which is my favorite. And I had so many examples here I had to put because the question is, suppose you have a triangle with one median without constructing the other, how can you find the centroid? And this is the one where you saw how each median was split into 2 and 1 or 2/3 rule. So the one in red is not right. This is the one where you'd maybe pause or go find that student and say, listen, you wrote half the median. It's definitely not halfway down the line, right? But these other students here very concisely summed it up. You would go 2/3 into the triangle from each angle. And again, the point is they're going in from the angle, not from the base, right? That's an important part. Side note, a big part of also the geometry you see is segment partition. And the other 3 students really sum up that segment partition. They say you can split the line into 3 portions and plot the centroids 2/3 of the way. Again, that's definitely like line segment partition. Or from the vertex to the midpoint, divide the median by 3 and multiply by 2. And in my classroom, I always like to point out lots of different ways to do these problems or any problem, because in mathematics, there is not one right way most of the time. So I like that everyone is sharing their ideas. You can project this up for the class with anonymous names and say, this is all different ways to say the same thing, because sometimes they learn better from their peers. So it's almost like student-based learning here. So when you go to the lesson, you could screenshot this page and be like, here, how can you summarize the rule, right? You can use the student, what they say to teach your lesson. And then the last student just said you can locate the centroid by trisecting the median, where the centroid is 1 from the side and 2 from the vertex. Okay. So that is all the student data I have that I chose. I'm going to put that to the side. And then this one is just a picture of the Euler line again. And links back to the actual book, but I did that already, so I'm not actually going to click on anymore. And then the last time I was making this, I taught about improvements, and I was going through this because I teach geometry only in the fall semester. My school only offers it in the fall, and they take their EOC in December. So I as I was going this, I was like, man, I got a lot of things I can improve. One of the things I mentioned earlier was to change it so after one picture, you only have 2 questions. You don't have to scroll up and down, especially with the iPad. And by the way, doing GeoGebra on the iPad is really different from the desktop. So when I demonstrate things with my students, I always try to teach it to them on the iPad, but it still works great. It's just different. So this was, I said in the very beginning, was a loose interpretation. Like the proofs were loose. They just showed the parallel lines. They would show that the opposite reciprocals, right? So then they form a 90-degree angle. So they're perpendicular. That was a huge one, show perpendicular lines with opposite reciprocals. But to go back after learning the modular and quadrilaterals, because I did this before, and add in the formal proof. So go back to that original, the original coordinate geometry one, and add activities at the end, right? And then you can share it with them. So the link, so when you update it in real time, they'll get the updates. Where now they know if, the rectangles are the diagonals are congruent, or, the diagonals bisect each other, or, all these different properties of kites and rhombi and trapezoids. You can put in a formal proof, and that could be your assessment at the end. Then you just click on the last one of the book or the activity, and you look, hey, what's their proof look like? Do they have diagonals bisect each other, or the diagonals are perpendicular, therefore it's a blah, 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 You could even do, and again, I just made this up, when Ed showed the idea of doing a little graphic charts, you could do them where they organize the shapes. How does the quadrilaterals, how do the rhombi, the rectangle, square all fit in relation to all quadrilaterals? And again, that would be a very informal assessment. The other thing I would like to add is a buy-in or hook at the beginning. Like the first presenter of the day, they had the one with R2 and C3PO, something to hook them into it. This is an exploration, so it's not a lesson, student-based learning, but you still want to hook why they would do it. And last I would do is, I think students could all do this, is have groups recreate these activities, like the one about the parallelogram rectangle, but tailor it to kites, rhombi, and trapezoid. Have them make the activity, which they certainly can, because all you have to do is show them how to do it once, and they are experts at technology. So you say, open up the activity, click add this, change the words. All they do is change it from rectangle to rhombi, and then they could trade and complete each other. So that would be like a higher level one, right? And then provide an answer key, clearly. So that is the last slide of my presentation. So I will stop sharing there. And I know we're a little bit early.
Wonderful. Thank you so much, Sarah. Thank you so much. I think it was very valuable to hear from the teacher, and from the point of view of teacher who's using the classroom and sharing your experience, how students are reacting, how you can use this, all kinds of information. Yes, this is like the tools. GeoGebra is a beautiful tool, but it's as good as we use it. Yes.
Yes, that's right. It's good because we use it. Exactly.
Yes. Thank you so much for your valuable. I share again the link to your presentation, and definitely we are looking forward, seeing you next year. I hope.
Yes, of
maybe
course.
a workshop.
I love it. Yeah, no, I'm not on Twitter. Sorry. I'm like I said,
no, not everybody has to be on Twitter. For me, Twitter is too short.
Yeah, exactly. Yes. Thank you, everyone. I really appreciate it.
Thank you so much. And now let's have a 10 minutes break before next one. It's a 10 minutes lunch break, and we will have Karen, if I remember, yes, at 1 p.m. Thank you so much, Sarah. Again, you really grew. You were my students, and I'm so happy. You took something from
I made it in your class. The book I made in your class.
You are a wonderful example of a MST student at FAU. We all have like students like that. Yes.
Yes.
Thank you very much. Thank you for sharing. And everybody, we are finishing that, and move to the lobby, and then let's see you at the next presentation. Thank you. Thank you.